I want to play a little sound. All right, so just kind of sit back, relax, close your eyes, and listen to this sound. So what was that sound? Surprise, surprise, that was the sound of the Big Bang. And this image I'm showing you here is our earliest snapshot of the early universe, okay? About 380,000 years after what we call the Big Bang. Yes?
Wait, how did you guys get that sound?
Aha, good question. So, in a nutshell, this figure here, let's say just take kind of just a step back and we'll answer that in this method. So check it out. This image here, like I mentioned, is a snapshot taken 380,000 years after the Big Bang. The universe is still incredibly hot and incredibly dense and expanded. Okay. Now, how we got that waveform? This map here is showing temperature anisotropies, meaning the red dots are places of higher density, the blue dots are places of lower density. That's all you need to know for now. And the differences between the hot and cold spots are actually incredibly small. But there's so much we can talk about in just that, that one factor, this one map. But to answer your question, these are temperature anisotropies. From this, you can do a little bit of physics and turn them into an angular frequency spectrum, also known as a multipole spectrum. And from that, it's not too hard to get to a frequency spectrum, which is essentially sound. Now, as for what's the reality of that? I don't get it. This image is static, and that noise was moving. Yes. So from this one snapshot, we get the spectrum, which is like a snapshot of a sound wave. Like you ring a bell, like that 1 second, or once that bell is ringing, or sometime after, some snapshot. That's what you see here. It's then extrapolated back in time to the early universe, the Big Bang, so 380,000 years earlier, and then out into the future, specifically about 750,000 years after the Big Bang. Okay, and that's why you hear it kind of getting lower and lower and lower, because the early universe was really hot, really dense, and more importantly, for our case right here, supported sound waves. Just like this room right here, supports sound waves, you can hear me. But as you all probably know, if you go out to space, you can't really hear any sound, because vacuum doesn't support sound waves, right? So you're like, wait a minute, but the universe, I thought doesn't do this, right? Well, in the early universe, things were a lot closer together, meaning a lot denser, essentially like an atmosphere. Sound waves could travel. Now, if you were there as a human, just chilling, hey, early universe, what's going on? That frequency, that sound, would be permeating the entire universe. And as it's getting bigger and bigger and bigger, that wave is getting stretched lower and lower and lower. However, one thing I didn't tell you, which I'm going to tell you right now, is that frequency, you wouldn't be able to hear with your human ears, because it's so damn low. In fact, the actual frequency had to be boosted by a factor of 10 to 26, which I don't even know the number. Some of you might know that. I don't know. Whatever that is, it's huge. Okay. Only then can it be brought up to our audible frequency grade. Does that answer your question? Cool. All right. Thank you. That's a good question. All right. So that is the sound of the Big Bang. Holy hell. Moving on. All right. Got one more sound for you. What about this sound? What was that? Exactly. A dish breaking. So, all right. What the hell's going on? What did I walk into here? We got sounds of the Big Bang. We got sounds of dishes breaking. How are these things connected? Well, I'm going to show you. And just like this dish was connected back together using this gold solder, using the method known as Kintsugi, we will see some connections taking shape. So this right here is a beautiful example of this Kinsugi technique. Okay? So let's talk a little bit about this. And like I just said, we're going to see how they're related by talking about what Kintsugi is. So real quick, art history, digression. Essentially, Kintsugi can be thought of as an art, a philosophy. The main gist is if you have something that you cherish, that is breakable, in this case, ceramics, and then it breaks, okay? Usually people think, oh, it's broken, let's toss it, or oh, I'm so sad. But Kintsugi actually embraces the impermanence of nature. It knows, it's taken for, a fact that this is part of nature. Impermanence, broken symmetry, and more importantly, highlighting the fix. Usually when things are broken and then fixed, people try to hide it, like a tailor or whatever. They try to hide the fix. But this is very different. It's the exact opposite. They're highlighting the fix to show how beautiful it is. So with that said, Shogun Ashikaga Yoshimasa, he was in Kyoto. He was actually living at the Silver Pavilion. This is a picture of the Golden Pavilion, just because it's slightly more photogenic, but both are quite good. And so this, like I mentioned, is related to the philosophy in Japan of wabi-sabi, which is essentially this idea of embracing the impermanence of matter. When people say wabi-sabi, they kind of mean like something beautiful but sad. So for example, like an autumn leaf, or like, an autumn leaf falling off a tree. That's like a very wabi-sabi thing. You can take a nice picture, it's beautiful, but a little sad, So that's just a little introduction there. Now there are actually 3 different kinds of Kintsugi techniques to fix a broken dish. The first, most basic one, which you've already seen, is this style known as the crack method, which is the simplest. You have all the pieces that broke, and then you just kind of put them all back together using the gold solder. Pretty good. Beautiful. The next method is called the piece method. This is, one piece or maybe more pieces are missing, but you can use the gold solder to kind of fill in that missing section. And as you can see, I don't know about you guys, beauty's in the eye of the beholder and all, but I think this stuff is looking more beautiful than it was before, personally. But don't worry, we got one more. The joint call method. This is just like the piece method, except you actually use a different piece of a different dish that looks about the same shape. And then you kind of pop it in and do the Kinsugi with it. Okay. And so, this started, like I said, about 500 years ago, and it's just kind of always stayed around, and recently it's kind of gotten a resurgence. Even like in America, there are places that do this. Of course, in Japan, you can find a lot of places that, like, if you're a tourist, even you can like go for a day and do learn Kintsugi, stuff like that. So, with that said, we now want to go from this idea of Kintsugi and bring it back to space-time. And specifically, the main point I want to start here with is that Kintsugi would not exist without the breaking of symmetry. In this case, when I say broken symmetry, I mean like a dish is approximately symmetric. All right, I'm like a cosmologist, and cosmologists, we like to approximate. So, I'm going to say, most dishes are more or less symmetrical. Okay. Granted, there might be small imperfections here and there, but you get my point. And so it needs to break in order to do Kintsugi. You can't be doing Kintsugi on something that's not broken. So in that sense, I think of Kintsugi as relying upon broken symmetry. Likewise, and as we'll show in the rest of this talk today, both the origin and the fate of the universe might also depend upon broken symmetry. And that is how they all might be related. So, let's dive in. Any questions so far? While I take a sip of my tea. Nothing? Okay, good. Okay, so check it out. We're going to start with the origin of the universe, otherwise known as inflation or the Big Bang. I want to be a little careful because sometimes people, there's this little terminology issue with Big Bang, inflation, which one happened first. I'm going to say it this way, and this is maybe not what your textbooks say exactly in the order, but this is what the research says, actually in the papers. Well, actually, no, hold that thought. We'll get to it. Let's start very simple. Inflation / Big Bang, all right, is our current cosmological belief or theory, framework of how the universe that we see today came into being. And sometimes inflation is known as the ultimate free lunch, because from the emptiness of space, the empty vacuum, we got everything that we see today. Okay, this pizza behind me, this room, okay, the lunch you might go eat, the leaves you were looking at, the flowers, your girlfriends, boyfriends, everything. That all came, if you track it back down to the emptiness of space. Space phone, quantum phone, okay? And this is what inflation talks about, okay? So now you're starting to maybe get a little, this sounds a little crazy. I'm intrigued. Well, where does inflation fit into the big cosmological picture? Okay. You've probably all heard of the Big Bang. Well, quick show of hands, actually, I'm a little curious. Before you walked in today, who had heard of inflation before, in the sense of cosmology? It's only a few people. But who's heard of the Big Bang? Pretty much everyone. And I can then assume that if you've heard of the Big Bang, you pretty much know, Big Bang, the universe is getting bigger and bigger, right? That's kind of what everyone's kind of the impression of, more or less. Okay, well, it doesn't matter. I'll explain it right now. So yeah, so basically, this idea of inflation fits into our cosmological picture like so. It's believed that our universe began 13.8 approximately billion years ago. This is a little bit old. It's a couple years old. I probably should update that. Okay. In this event known as inflation. Okay. The universe started infinitesimally small, started inflating, getting bigger and bigger and bigger. Eventually, it cooled down enough to give us this surface of black scattering known as the CMB, which is the picture that I showed you before. Okay. And that's that right there. 380,000 years after the Big Bang, or inflation as we're saying now. Then essentially the universe was getting bigger and bigger and bigger, but it was slowing down. Okay. Then you had galaxy formation, structure formation, large-scale structure, all these stars, all these galaxies, all this beauty all around us forming. The universe is getting bigger and bigger and bigger, slowing down, slowing down, slowing down, until we get to right around approximately today. And then suddenly the universe starts accelerating. And this is the idea of dark energy that some of you all might have heard of. That was first observed, very shockingly, back around 1998, so about 20 some odd years ago. Okay, so this is still very fresh, still very new. Wmap Satellite, this is the Planck satellite. These are two satellites that measured the CMB image that I showed you. And you know, CMB can, like I mentioned, be a whole talk on its own and be a great talk. But the point is, the CMB was first observed back in like late 80s, early 90s, and it's only been getting better and better and better. Wmap was back in the 2000s. Planck was, we got the data in 2013. Okay, so this is also still very recent. And in fact, the image of the CMB that we got from Planck is the best possible image that we'll ever get of CMB. I don't mean like, oh, like, you know, like it's just the best we can do now. I mean like, it's so good, it's limited by physics. We cannot build a better, it's not possible with the physics that we have to build a better observational instrument of the CMB than we have at Planck.
Cosmic microwave background.
Yes, I'm sorry, if I finally, yes, thank you. Cosmic microwave background, the CMB. Okay. Anyway, but we don't want to get too deep into this because we have more to talk about, mainly inflation. But if you have any questions, of course, save them for later. Okay. And if you have any questions along the way, I'm going too fast. Feel free to just interject, slow me down. No question is bad. So, any questions so far? So, with that said, Big Bang is obviously more popular, you know, in terms of just like a name. People know more about it. So let me just kind of give you a quick breakdown of where it came from, like in 30 seconds. Essentially, the Big Bang idea was around for more or less decades, kind of kicking around here. We had Einstein, he gave us general relativity back in 1915. Soon after that, we got some equations from that theory that described the evolution of the universe, which gave birth to our cosmological theories that we have today. And then this idea of an expanding universe from a central point started soon after that. Okay? And that's kind of where people started thinking about this Big Bang idea. Eventually, we had the CMB. It was discovered back in the 60s, actually. Okay, it was first discovered on Earth as a very low hum. But I don't want to get too deep, sorry, into the details. But the point is, at right around the 60s, it became pretty definitively known that, okay, this Big Bang idea, you know, there's always a battle, like, oh, we like the Big Bang. And people are like, no, Big Bang sucks. We like steady state theory, you know, and they fight. And ultimately, they need data to resolve the conflict. And once we had that observation of the CMB taken from Earth, the satellites I showed before, you know, in space, from Earth, it's a much lower resolution, but it was first taken back in the 60s. Okay? That was what definitively cemented the idea of the Big Bang. It's like, wow, this really works. And then for the next couple decades or whatever, that was like the forefront of like how we thought the universe started. Okay, so that's the Big Bang in a nutshell, historically. However, there were three big problems with it. Three very big problems. One was called the horizon problem. And the idea behind that is that if you look at the CMB image, you can think of the CMB as like a bubble surrounding the entire universe around you at like the furthest edge, if you will, okay? And so everywhere you look out into the universe, the furthest edge of the universe, there are photons coming to you from the early universe, okay? But the point is, the universe is huge. And I kind of alluded to in that first slide or two that these temperature differences are incredibly small. Like on the fraction of, like on the order of 10 to the negative 5. Okay, which is incredibly tiny. What I mean to say is, these are essentially the same temperature. Anywhere you look in the sky, they're all about 2.7 Kelvin. So maybe if you look there, it's like 2.700001 Kelvin, but if you look in, right next to it, it's like 2.07 or 69999. It's all really close to 2.7. Okay, incredibly close. But wait a minute. We might know enough about heat and thermodynamics to say, well, that sounds like something's thermalized. Came to kind of thermal equilibrium. All right. How could that be if they, weren't in contact, right? What's the deal here? There's also, if you look at the details of actually the horizon and the physics from general relativity, there's a problem of why is the CMB so uniform? Okay. The Big Bang idea kind of gets you close to it, but there are technical details that need to be filled in, and inflation solves those problems. Okay, and we'll talk about how in a moment. Second is the flatness problem. Why does it appear to be so flat? Ultimately, real quick, observations have shown us that the universe appears to be flat, approximately. I'll just leave it at that. But that's a bit weird, because in order for the universe to be flat, it's like a very, very special condition. Essentially, it's like an equilibrium point on top of like an unstable equilibrium. All right, unstable equilibrium point is cool, like balance. It's like taking a pencil and balancing it on its point and letting it stay there for 13.8 billion years. Very unlikely. Okay. So the question is, well, if the universe appears to be flat, how the hell did it stay flat for 13.8 billion years? Okay. So inflation solved that. Third problem is this magnetic monopole problem, which is a little, it's a kind of a subtle thing, but essentially, Big Bang theories predict, not predict, I should say, but they use high energy physics. Okay, obviously there's high energy physics going on. It's the early universe. You have brand new time theories. You have things. You have electroweak forces. Coming together. Coming out of existence. You got the gravitational forces, strong forces, weak forces. Point is, these are all considered grand unified theories. Okay, and one, corollary of grand unified theory is the production of magnetic monopoles. Not even just like one or two, but like a lot. Meaning, based on the physics of what people were playing with the Big Bang back in like the 70s, they were expecting to see like more than a million. More magnetic monopoles than there were like atoms in the whole universe. But when you actually look, you know how many you see? That's right, 0. 0. So we observed no magnetic monopoles. And this is very mysterious because what's going on? Because obviously we should be seeing them. We don't. So these were the 3 big problems that inflation set out to solve to save the Big Bang theory. And again, this is around the late 70s, early 80s. Okay. Now, the first working theory of inflation that came out was back in 1981 by Alan Guth, currently at MIT. We're not going to go now. What I'm going to try to do here is I'm going to try to kind of just tell a story using mostly pictures and not so much math. So we're going to kind of do this a little bit qualitatively. Just try to kind of sit back, relax. Of course, if you have questions, let me know. But this is kind of akin to it's a bit interesting in physics where sometimes to do really sort of high energy, sort of physics, you can get a lot done with just pictures. So for example, Vineman Diagrams, maybe you've heard of these before. Well, anyway, those are just little figures that convey a lot of information and save a lot of calculations. So we're going to try to do something similar by looking at these potential diagrams for different inflationary models. And then we can get a very nice intuitive picture of how physicists were thinking about the early universe back when they were doing this. So this plot here is just essentially a potential energy diagram. You have the potential energy V on the y-axis, and you have this parameter phi on the x-axis. Just think of phi as a spatial parameter now. If you want to make a note, you can think of phi also as what's called an inflaton particle. But we'll get to that later. Don't worry about it. And you can just think of this potential as having a variety of different shapes. Okay, this is one particular shape. It could be a parabola, could be whatever. Pick your favorite quadratic form, whatever. Okay, and this right here is a particle, which we're going to think of as an inflaton particle, just some hypothetical particle. Okay, and think of it like a marble in a bowl. Okay, and you can start thinking of what to expect from the physics. Okay, so what I mean is, in this case, there's a couple important things going on. This false vacuum and a true vacuum. True vacuum is just defined as where the potential energy for the global system is actually 0. So in this case, it's actually 0, so therefore this is called a true vacuum. However, over here, where this potential has kind of this little local dip, this particle, when it's sitting there, from its perspective, not moving in this local potential minimum, it doesn't know it's not the true vacuum. It thinks it's there. So that's why it's called a false vacuum. Okay, that's all it is. It sounds a little fancy, but that's all it means. And specifically what Alan Guth showed was that if you had a potential of this form, and then if you had a particle that happened to quantum mechanically tunnel through the potential barrier to the true vacuum, and then if you worked out the resulting physics and the calculations behind it, which he did in this paper that you can go look up, then you can get inflation. And it will solve all three of those cosmological problems. Okay? However, this first iteration of inflation didn't work. The main problem is it never ended. It's called the Graceful exit problem. It never ended. Just kept going. So, good start, good form, but ultimately wasn't right. Next, about a year or two later, in this case 1 year later, there was a slightly better idea put forward by Albrecht and Steinhardt. They were both at Princeton at the time, and they just took a slightly different potential form, and they said, okay. What about if we have an inflaton particle here, and just like a marble on like a, in some bowl or whatever, this is an unstable equilibrium. Any deviation is going to roll down. Okay. And now, in the framework of this idea of inflation and these figures, when the inflaton rolls slowly enough, and there's a reason why it has to be slow, you get inflation. So this model here worked, and it stopped. So it solved the problems of the Big Bang cosmology. It had a graceful exit, all good so far, but it didn't really sit right with physicists. So, a year later, Andre Linde, working out of Russia, he was like, I got it. We're going to give it a really complicated name for a really simple process. Chaotic inflation uses just a very simple parabolic protection, just like this. And it says, okay, that problem about the particle starting somewhere unnatural, forget about it. It starts here at the center, at the true vacuum, 0 something. Okay? Then the next question, well, how do you get it rolling? Easy. Quantum fluctuations. Early universe, you got lots of quantum fluctuations. Before I said, and we all kind of think that the vacuum is empty. Wrong, vacuum's not empty. Okay? You want to read about that? There's a really good essay by Asimov, all right? Isaac Asimov. Point is, empty vacuum is a very hard thing to truly find. And in the vacuum, you have quantum fluctuations and virtual particles and all this stuff going on. So the point is, if you have a little particle in the early universe just kind of chilling here, there are quantum fluctuations going on all the time of different orders of height and whatever. So you could potentially get a quantum fluctuation that will kick it up initially high enough where it's going to roll back down, but slow enough to give you inflation. So I know this might sound all a little wild and crazy, but does the general idea sort of make sense? Just like having a marble in a well. If there's a little bit of a deviation, a little bit of a push, it's going to go up. And then when the push is gone, it's going to come back down. And if you work out the physics, you can actually make predictions. This is what's amazing about theoretical physics. From just starting with these very simple assumptions and plain models, you can actually calculate some really big results, and more importantly, observables. They can then go out and measure, which we've been doing. So in this particular case, the potential that Andre Linde chose was what's called a 1/2 m squared phi squared potential, otherwise known as y equals x squared. That's it. And the beauty behind this, and this is just like Glenn's comment before, it could be any potential, really, as long as there's a region flat enough for the marble or inflaton to roll slow enough. Okay? And then at this point, you kind of just got to take my word on that for now. I will show you some stuff in a moment, but we're going to talk about it later. Anyway, this is just another figure showing the quantum fluctuations. They could be small, they could be large, so on and so forth. You can look up the paper here if you want to check out the details. Okay? Now, what I find beautiful about this whole argument, though, is that what it's kind of saying, if you take a step back and think about it, is like, wait a minute. You're telling me that something as simple as a parabola can literally determine the fate of the universe in terms of inflation. Because that's really what this comes down to, man. Inflation now, like the current research on inflation, is just like the search for the right potential. Like, what is that potential? In fact, there's a paper came out a couple years ago called like Encyclopedia Inflationaria, and it like surveys like every inflationary theory out there. There's like over 300, I believe, in that paper. And that was written like 6 years ago, so there's probably like another 300 now, okay? And they're all just trying to work out different potentials and different ramifications of that, okay?
Is there any other area of physics that ever predicted some form of inflation by people who are not concerned with the horizon?
Particle physics. Yeah, particle physics. I don't know the exact context of what they were doing in the high energy physics, but that was the whole thing with Alan Guth of how we actually got the idea. Because he was at SLAC at Stanford, which is the Stanford Linear Accelerator, Collider or something like that. Whatever. Point is, he was in a particle physics community. And they were discussing the super cool phase and exponential expansion stuff. And then he was like, huh. And actually saw a really cool thing just this morning when I was looking up the figures for this talk, or it's actually a notebook, a picture of his notebook, where he writes down, like in 1979, December 7, 1979, what was it? Fantastic realization, hyphen, and then he explains this, just like in a paragraph of like, yeah, based on the talk I went to the other day from, this guy, these talks, I think this could actually work. Let's make an assumption. Let's work it out. And then he does. And then 2 years later, he has a paper, and now he's like, so, theoretical physics, what?
What's your age coming from in the equation question?
Oh, good question, great question. So real quick, I want to we can talk about this later because it's just a little bit technical. This is called the Klein equation. It's an equation of motion for the inflaton particle. The h here is the Hubble parameter. So the same h that we're kind of familiar with, Hubble parameter, that's Hubble parameter. Okay. But this is a differential equation, so some of you have taken differential equations. Second order, linear, constant coefficient, differential equation. So good, we'll talk more about that later. But cool. So, whoa, oh my God, what's going on here? Look at all this math. Don't worry about it, okay? I'm only gonna show you this slide in the next 2 slides, just to kind of give you, I've only been showing you pictures. Now, don't worry about this. The whole point here is, everything we've been talking about is calculable, okay? Everything is calculable and can make predictions. And these are the predictions that we then go out, one of them that we then go out to observe using these satellites, using these cosmic microwave background radiation maps, okay? We then look for this thing called the scalar power spectrum. Again, it doesn't really matter, but look, lo and behold, potential, is in this A term, which is the front term here. And then you have these slower parameters, which also all depend on B. Point is, the potential is incredibly important. Okay, we're not gonna work this out, it doesn't matter, don't worry about it. Point is, this is all calculable, and it all depends on B. You have the scalar power spectrum, you got the tensor power spectrum, you take them together, what do you get? You get the tensor-scalar ratio, okay? What is that? Don't worry about it. Point is, it's calculable, and it's observable. And when you boil all this stuff down, guess what it equals? 8 over n. What the hell is n? N is the number of e-folds of inflation. What is an e-fold? An e-fold is just what we call like an exponential expanding of the universe. I'm sorry, I'm totally botching it. An e-folding is essentially when the universe gets bigger by a factor of e. Okay. Now, in the early universe of inflation, it's considered that the universe got a factor of e to the 60 times bigger, where e is Euler's constant, 2.7, whatever it is. Okay. This is not very intuitive though. Physicists like to do kind of unintuitive things, kind of just mess with people. This is essentially equivalent to 10 to the 26, base 10. Okay. So meaning that during the epoch of inflation, the universe got 10 to the positive 26 times bigger, which is huge. Actually, oddly enough, it's the same factor that we had to boost that frequency to get the sound of Big Bang up to our frequencies range. What else? One thing I didn't mention real quick, I'm sorry if I'm going a little bit too fast, is that this whole exponential inflation happened during a time frame of like, literally like 10 to the negative 36 to like 10 to the negative 35. It was just like super quick. Like fraction of a second, huge exponential expansion.
The expansion of the universe was already taking place for a time.
Well, it was, in this case, this is where I don't want to we can talk about this later because we can get into the weeds here. But essentially, we're going to say inflation, well not we are going to say this is what it is. Inflation sets up the initial conditions of the Big Bang. So from inflation, you get what's called reheating. We can talk about it later after the talk. And then from that reheating, you get what's called this hot Big Bang, otherwise known as Big Bang. And that's where the Big Bang as we know it technically starts. Okay? And that's why I say inflation sets up the initial conditions for the Big Bang.
What's the second word?
Oh, reheating. Yeah, so I won't go into this right now, but we can talk about it later. We can look it up.
The color of it.
Oh, sorry. Yeah, tell me
The
color.
slide's better.
Thank you. We're gonna use white. Okay. But the point that I want to stress here before we get too off topic is that no worries, is that it's 8 over n, where n is the number of e-folds, and the e-fold also is open to observations and interpretation because if you have too much inflation, it messes with large-scale structure. If you have too little, likewise, you get not enough. So the e-folding is kind of constrained around 60. But sometimes it could be 50, it could be 60. There's a little bit of leeway there. Okay. So anyway, but that's all it is. So this tensor-scalar ratio, which is an observable, equals just 8 over n. Which, if you do 8 divided by 60, it's approximately 0.1. Now this figure here, I'm only showing you to show you that this was the result. when we actually took that Planck satellite, put it up in space, got the CMB spectrum, looked at all the different data we could get from it, and then calculated the tensor to scalar ratio and this primordial tilt parameter, don't worry about it. Point is, this was the snapshot taken in 2013, okay? And lo and behold, well, actually, before we get to the result, I just want to show you the evolution of this figure and this number. Because check it out. The first measurements weren't really done until 2005, okay? And when they were first done, our constraints were, well, it's less than 0.71. Then a couple years later, it's less than 0.43. A couple years after that, 0.28, 0.18, until a couple years ago, 0.11. So in literally less than 10 years, we've really batted it down quite a bit. And it's really quite close to what we were expecting. So the reason, though, that this all becomes interesting and related to our talk now is that, oddly enough, although for many decades, inflationary cosmologists thought counting inflation worked the best, when we got these results from Planck, suddenly hilltop inflation looked like it fit the data the best, which was a shock. And I'll just leave it at that. Okay. So, hilltop, you're like, wait a minute. That sounds a lot like that hilltop inflation kind of thing that I saw before. And how does it work back to what we're talking about today? Well, check it out. This hilltop potential is an example of symmetry breaking in physics. Okay? So this potential that appears to be the best fit for our current model of the origin of the universe, all right, comes from broken symmetry. And if this looks kind of familiar, you might have heard what's called like the Mexican hat potential or the Higgs potential. Okay, you've all heard of the Higgs particle. Well, guess what? If this all sounds crazy, like, whoa, like this sounds totally ridiculous, like this is a joke. Well, guess what? Higgs particle? Same deal, folks. Same deal. All right? There's a scalar field permeating all of space called the Higgs field. And that Higgs field has a potential. What does it look like? It looks like this. And what's the Higgs particle? Same thing as the inflaton here. Just a particle that has dynamics. Okay? Mediates force, in this case mass. So this sounds crazy. Guess what? Nobel Prize committee didn't think it was too crazy to have a permeating scalar field. It was a Higgs field. Another example of broken symmetry. Maybe for another iteration of time. Okay? So this is beautiful. Okay? Interesting. Very interesting. Okay? Now that's the origin of the universe. Okay? Now for the second half of the talk, this brought us from the origin of the universe up to today. Okay? Cuyamaca College. But now we want to talk a little bit about the fate of the universe and see how that also might be related to broken symmetry and inflation and ultimately Kinsugi. Okay? But in order to talk about the evolution of the whole universe, let's kind of just see what we really mean by that. Okay? In terms of just like, let's just take inventory. All right? So real quick tour for those of you who haven't taken Astro 101 with Glenn here or somewhere else. We're here at, lovely, beautiful Cosmology College. And if we, this is today. And if we kind of just go up a little bit, we see it from above. We go a little bit further out. We start seeing the Earth, the curvature of the Earth. All right, a little further out. No surprise, we see the Earth, the Moon, the Sun. Okay, very familiar, very familiar. All right, we're all in our comfort zone. So far, so good. Got the solar system. We got the Milky Way. You all know that the Sun is just a star, and the Milky Way somewhere here, and the Earth's going around there. So we're just moving out, out, out. But of course, our galaxy, all right, is only one galaxy of many. In this case, many in what's called the local group of galaxies. Maybe we're like right there, if you want to pick one. Of course, we can't see ourselves there. And if you keep going out and going out and going out, you got bigger groups of galaxies and so on and so forth. You have what's called the Hubble Deep Field, all right, which is one of the most beautiful images taken. Maybe at the risk of digressing. Quick question, how many individual stars do you see in this image?
A lot.
Okay. Any guesses?
I would say probably like 1 billion stars.
Pretty good, pretty good. Any other guesses? Individual stars, individual stars.
Well, I see something I'm looking for something with spikes.
That's right, that's right. So, in fact, in this image right here, the Hubble Deep Field, one of the deepest, it is the deepest optical image ever taken, okay? Using the Hubble Space Telescope, there were only 1, 2, 3 stars. Maybe one more hiding somewhere else. everything else that you see here is a galaxy. So if you're like, whoa, wait a minute, whoa, I don't get it, what's going on? Well,
when we come here, we see a little, not many, little.
some of it, yeah, exactly. It's very
As
little.
the picture, when I come, I see.
That's right.
When I go back, I see more.
Well, in this case, it actually was coming down. The other day I was at the beach, and I had some sand in my pocket. I have right here, 1 grain of sand. You can all see that, yeah? And if I take this grain of sand, I very gently hold it up to the sky at arm's length. You see the surface area that it covers?
Yeah.
That is the size of this image. Boom. So that's why there's only 3 stars in the whole image. Because it's so small. But in that little image, you see all these galaxies in it. And you know from our experience with the Milky Way, that in just one galaxy, you have so many stars, and so much Venus, so many things. And so now you start thinking, wait a minute, if we have this many galaxies in 1 grain of sand, and how many grains of sand might be in the whole sky, then multiply that with the number of galaxies count in this image, like holy, and then how many stars are in each galaxy, you start getting a kind of an approximation of just how much stuff there might be in the universe. And all this stuff.
What amazing color contrast.
Yeah. All right, so anyway, I'm sorry, a little bit of a digression. Moving on, because we're not done yet. Remember, we're moving out, man. We're moving way out to as far as the universe. All right, so we keep going out further and further and further. We start seeing what's called large-scale structure. All right. These bright spots here are all giant galaxy clusters. All right, just grouped together into like long, spindles or whatever it's called. All right, and if you go out further and further and further, you just keep seeing more and more and more of this. Now this was not actually what's up.
More details.
Yeah. You just keep seeing more of this web, just like all around you. All right, which is large scale structure. Okay. And we're somewhere, the Milky Way galaxy and the low group and all that, we're just somewhere in there. Okay. So, where was I going with this? Oh yes. So, question now is, okay. Well, this is all very interesting. So, this is our current kind of picture of the universe. Okay. And specifically, if we kind of took inventory of everything that's in there and kind of just really boiled it down, we would see that in that entire image of, like, let's just say the whole universe of large-scale structure, all right, there's only 3 things, okay? Dark matter, dark energy, and everything else. Now, again, I'm sorry, we don't have really time to dive into, the deal of what dark energy is and what's dark matter. We can talk about it after the talk or in the future, whatever. But the point is, it's been shown conclusively that our universe is composed of 20% approximately dark matter. This is kind of an old figure, I should probably update it too. 70% dark energy. That's, we're going to see, is very important for the evolution of the universe. And everything else, everything that you've ever seen. No, I should state something that might not be known. We call this dark matter and dark energy because A, we have no idea what it is, and B, we don't see it. Meaning, when I look out into the universe, 96% of it ain't there for me, for my eyes. Only 4% is everything else that you've ever seen, ever felt, ever loved, and ever will. You will never see anything else beyond that 4%. But yet, all that beauty, Cuyamaca College, the Earth, local group, Milky Way, large-scale structure, all that, man, you're only seeing 4% of the picture. There's 96% more stuff that you ain't seeing. It's like having a pepperoni pizza. I'm from New York, so I use a lot of pizzas in my talks. That's all the time people know that. Yes. So, if you have pepperoni pizza, this is like only having altogether maybe like less than 1 pepperoni out of the entire pie. I'll just leave it at that. Okay. We got to stop talking about it. Point is though, dark energy is important. Keep it in your back pocket. We're gonna get to it in a moment. Okay, so that's our inventory today of like what's going on in the universe after inflation. All right, we got a lot of stuff going on. It's beautiful. We're only seeing 4%, and there's a lot of dark energy. Okay, so some of you might have gone outside last night. Maybe Glenn, you had a field trip. Maybe you all looked at the stars. You might have seen something that looked a little bit like this. Okay, pretty cool, pretty cool. Astronomers are all about patience. We have to be patient. So let's say you're really patient and you waited for like, 3 billion years. What might happen to that view? Well, hate to be the one to break it to you, but that view is going to change. Specifically, our closest neighboring galaxy, Andromeda, in that local group that I showed you earlier, is on a collision course to us. And in fact, in approximately 3 billion years, we're going to collide. Simple as that. It's gonna happen. Nothing can't avoid it. Rest assured, everything will be okay, and we can talk about this also later. The view will change, but ultimately we'll be okay. And the reason why is because the distance between stars is so great that the probability of two stars colliding is like the distance between, like the probability of having a marble in Texas and a marble in New York colliding. All right, very, very low likelihood. Yes.
You said two universes?
Two galaxies. Two
galaxies. Okay.
Yeah. Now, in terms of universe collisions, that could actually probably happen called a bubble collision, but that's separate. But that's a little interesting. Anyway, which could also be observed with the CMB.
Just for the benefit of my students, our galaxy seen from inside.
Yeah.
That's what's on the right.
That's
And
it.
Andromeda is going to come and get us on the left.
Yes. Yeah. So we're not going to actually see our galaxy. We're in the galaxy, but this is just exactly. So okay, the point is this is in 3 billion years. So it's like, all right, let's say you're a really, really, really patient observer. And let's say instead of waiting 3 times 10 to the 9 years, you waited 3 times 10 to the 90 years. What are you gonna see then?
I don't know. Maybe nothing.
That's right.
Yeah.
If, assuming that our current cosmological picture keeps doing what we think it's gonna be doing, which is open to debate, and we're gonna talk about this in the following slides, then the prediction is that in the future, everything's going to keep expanding and accelerating and getting further and further apart. Because remember, I mentioned back in 1998, when we did the observation, we realized for the first time, our universe is not decelerating, it's accelerating. It's getting bigger and bigger, faster and faster. Now, if that keeps happening, then all those galaxies that we saw like in large-scale structure,
Would be fine.
exactly. They're going to keep going further and further and further apart. Stars are going to die, and then even if they didn't die, they're going to get so far away that they're going to get redshifted out of the visible spectrum. Point is, if you're a really, really patient observer, in this current framework, also known as the cosmological constant cosmology framework, you might have maybe heard of that. The idea is that in the future we'll die a big freeze. The universe will just be dark. You won't see anything because everything's so far away. Okay. And we can see this with the figure shown here. On the y-axis, you have what's called the scale of the universe. Just think of that as just size, if you will. And then the x-axis, you have time. Okay. And this is like a cartoon, so don't worry about the units, which usually would be important. And essentially, at the origin, you have this Big Bang inflation. Is due to the dark energy, which we don't know what it is, but we know what its effect is. Same thing with dark matter. We don't know what the dark matter is, but we see its effects on galaxy mass. If you have a question about that, we'll talk about it later. But the point is this. This was a huge shock, like I mentioned. And now, if everything keeps going the way we think it will, with this constant dark energy, this cosmological constant, then the future of the universe will be this kind of just, big freeze. Okay? However, if the dark energy is not constant, and by not constant, I mean any deviation away from zero or constant, whatever, then you get a different cosmological output or result. For example, it could be a big rip. The universe could get infinitely large, all right, in a finite time, and so therefore it'll rip itself apart. Or it could be a big crunch. The acceleration could stop, and then suddenly the universe starts decelerating again and come back together, and eventually, boom, another Big Bang perhaps, all right? And there are models of this. One's called the ekpyrotic theory, all right, put out by actually Steinhardt. Remember that guy Steinhardt from Princeton? He's still at Princeton, and he's still kicking out theories, all right? He's actually kind of pissed because he lost to Goof and Monday. They kind of get more fame for it. So anyway, but there is a theory called ekpyrotic, and this is all about a cyclical universe. Some people don't really buy it, but whatever, it's out there. There's lots of ideas. Point is, we don't really know. And the main point I want to stress here, this is the key, is that the fate of the universe is determined by the nature of dark energy. We don't know what it is, but depending on its nature, that will determine the fate of the universe. Now, this figure, just like before, don't worry about the details. I only show you this to kind of give you a little bit of an idea of how scientists think about this in terms of observations. And another way of looking at it, this here, we call it fraction of energy density. Just think of this as composition of the universe. And then this axis here on the x-axis, this is just time. ln of a, don't worry about it. It's just time. Okay. And like I said, cosmologists love to approximate. And we like to think of the universe as being composed of only three constituents: radiation, matter, and vacuum. In the early universe, it was super hot, radiation dominated, but then as it got bigger and bigger and cooled, eventually the radiation got cooler and cooler, and then the matter started forming and then dominating. And we got that matter domination phase. That was like in the picture I showed you back in the beginning of the talk. We got that structure formation and galaxies and all this stuff coming, That was during the matter formation phase. But then right around today, which in this case is lambda equals 0, you get this epoch of vacuum domination starting. And because it's constant, it just goes up to 1 and stays there. This is what we call the cosmological constant picture. This W stands for the equation of state. It's a ratio of pressure to density. Doesn't matter. The important thing, though, is that this model only works if W, the equation of state, equals -1 exactly. Any deviation away from -1, no matter how small, means it's not constant dark energy. Means it's something else. Meaning it's a different fate of the universe. Okay? And now if you're wondering, how is this getting to what we were talking about before? We're almost there. Just check it out. There are models of dark energy known as dynamical dark energy, or quintessence. Okay, that says, what if the cosmological constant is not constant? What if it can vary? Okay? What if, just like, and if you're thinking, wait a minute, the universe is getting bigger and bigger, faster and faster, accelerating, it sounds a lot like inflation, you wouldn't be wrong. In fact, you'd be completely right. The physics behind the dark energy acceleration is very, very similar to the physics of inflation. Okay? So in this particular model of quintessence, remember before I showed you the constant dark energy? It just went up and was constant. If it was dynamical, just like a particle or a marble in a bowl, as it kind of oscillated around the center, you kind of get these wiggles. And those are the wiggles that you see there. So this is the result of a dynamical dark energy. Analogous to what we talked about before in inflation. Interestingly, this theory makes the exact same predictions about the past. Meaning, it's exactly equivalent to constant dark energy. Nothing changes. The only change is in the future. Because vacuum domination will eventually drop off and dissipate. Matter domination will come back again. And we could potentially get more structure formation. Or more importantly, the universe will still be around to see for an observer, potentially. So it's a very, very different fate of the universe. Okay? And so, without belaboring the point, the equations of motion are the same. The physics are the same. The only difference is this m parameter. Back in when I showed you potential, the 1/2 m² phi squared. All right, you can think of that as mass. That's the main difference. But otherwise, from a physical point of view, very, very similar. And from the calculations, also very, very similar. So just like before I showed you that figure with the parabola, something as simple as a parabola can determine the fate of the universe. That's exactly what I mean. Just like you can do it for inflation, you can do it for dark energy. Except instead of being, for inflation, it's like, well, you still want a little bit of curvature, it's all good. But dark energy can be thought of as just a special case of dynamical dark energy. If potential is like so flat or perfectly flat, then constant dark energy, cosmological constant, is just a special case of quintessence. Okay. So, point is, this looks just like the Mexican potential or the hilltop potential, and in fact, okay, although constant dark energy models, cosmic constant models, are more ubiquitous in physics, it doesn't mean that they're right. It just means that they have not been disproven yet. Okay? And if you actually look at the data that we have that constrains the dark energy as being constant, you would see pretty quickly that it's not quite as strong and robust as like popular science might lead you to believe. We're really clear on it, like just a little bit out into the universe, like not too far out. But once you start going really deep into the universe, we can't really constrain these models for cosmological constant. Meaning the data doesn't really tell us much. So there's a lot of it could be a lot of wiggle room, I want to say. So working within that wiggle room, there's a paper put out back in 2014 that used broken symmetry models to explain dark energy. Okay, same deal as before. Just think of it like a particle or a marble in a bowl, and the dynamics give you acceleration of the universe. Okay. So at this point, just kind of wrapping it up a little bit, we've seen 3 examples of broken symmetry in nature. we have dark energy, we have inflation, and we have Kinsugi. Okay. So the question now is, does perhaps nature prefer broken symmetry? And ultimately, I don't know. This is an interesting book, Symmetry in Biology. Just wanted to throw it up there. And I think I'll just kind of show this image to you real quick. You know, on the left you see here an image of the brain cell, a neuron. And on the right you see the universe. Interesting, is it not? The smallest of scales and the largest of scales appear strangely symmetrical. Or dare I say, a little bit of a broken symmetry. I don't know, a little different. I don't know. But pretty close, pretty interesting. So on that note, please allow me to say thank you very much.